This is Unit 3, Topic 5, Introduction to Confidence Intervals. So it is really here in this topic that we truly start statistics in its more technical pieces. In Unit 1, we definitely did statistical concepts, but it's now in this Topic 5, Unit 3, that we're actually doing calculations and the types of things that people expect from you when you say, oh, I can do some statistics on that. So first, as a reminder, there are two different categories of statistics. There are descriptive statistics, and they just describe data. They don't do anything besides just say what you already have. An example of this is graphs, measures of center, variation, relative standing, and so on. There's also inferential statistics, which is where we make predictions about the population based on the sample data, ultimately what we desire to do whenever we're doing statistics. So this is kind of redundant. It just says we're going to use sample data to make predictions because we don't really have any of those tools in our tool bag quite yet. So within inferential statistics, there are three different types. There are point estimates, which is a single number that is the best guess for a parameter. We've actually been finding point estimates this whole semester. We'll see what exactly that means in a bit. A confidence interval, which is a range of values based on sample data that estimate a parameter. This is ideally what we'd want to have, not just a point estimate alone. These two topics we cover in Unit 3, whereas lastly, hypothesis testing, they test a claim about a parameter using sample data, and this is going to be Units 4 and 5. This is really the essence of statistics. It's exactly how we want to answer any kind of question that is given to us. So hypothesis testing is really the heart of it all. So first, point estimates, we are considering them the basis of inferential statistics because if you remember way back into Unit 1, the goal of performing a sample is to obtain the population values such as mean, standard deviations, proportions, etc., without performing a census. And we also discussed, and some of you got to show, that the sample being selected well usually means that we target those population values, such as mean, standard deviation, proportions, almost exactly, even if we didn't perform a census. So once we perform a census, those means, standard deviations, whatever, those are the point estimates. So if you have a data set and you find the mean, well, that's your best guess for the population mean, especially if you've done a good job collecting your sample. But a point estimate alone isn't going to be everything because we've also shown that there's variation between samples. So I can do a random sample, you could do a random sample, and so could everybody else in STAT 2050 and 2070, and we could all end up with a completely different sample. Our means should be pretty close if we did a random sample, but what we need to do is acknowledge that our parameter we're targeting, but it's still just a single number that we obtained from our sample. So from this, we wish to do a confidence interval. So a confidence interval is good because instead of just saying, hey, you know, the mean, we think it's going to be 10, you can give sort of a span of values. And this kind of covers your butt, but that's not why you do it. The reason you give some wiggle room is to show the variation that can occur between different samples. So my example for this is say I want to meet somebody and I'm meeting them after school, which is always kind of risky because I have no idea what can happen at the end of the day. I can be almost to my car and have somebody run over and stop me and say, hey, you know, I got a quick question for you, or, you know, I could get a phone call, or I could lose track of time or something like that. So instead of giving somebody a, you know, an exact time like 3 o'clock, I might say, hey, you know, I'll be there from 2:50 to 3:10. If it's a formal meeting, that wouldn't be appropriate. But if I'm just meeting somebody for some reason and it's not, you know, unprofessional of me to do this, I might give them a time span. So in this case, that wiggle room is in 10 minutes. So 10 minutes surrounding that 3 o'clock. Well, of course, everything that we do needs to be calculated very technically, but the concept is still going to be exactly the same. So our best guess plus some wiggle room is the total essence of confidence intervals. So what we're going to do here is we're going to get really technical. There's going to be 2 new pictures and 3 new concepts that we're going to get. And we're not going to look at a specific example of constructing a confidence interval until the next topic. So for now, I ask that you just go through and do as best as you can with these 3 new concepts and 2 new pictures. But for now, they're going to be pretty vague until we actually get to an example. But the trade-off is that we don't really have any notes for the rest of this unit. So notes are usually the longer PowerPoints that I spend lots and lots of time talking on in the videos, and not as much time of you doing things. Well, for the next 4 topics, there's not really going to be much new to learn concept-wise. It's just going to be taking what we've learned and practicing it and putting it together. So those typically won't have videos along with them. But let's get started with our 3 new concepts and 2 pictures. So as we mentioned, confidence intervals are 2 numbers, and they're called a lower confidence interval estimate, or a lower estimate, and an upper estimate. They are associated with a confidence level and a significance level. So those are 2 out of our 3 new concepts. The confidence level is notated alpha. So this is a lowercase Greek letter. We're going to use alpha for the end of until the end of the course. So I recommend that you know and love alpha and know that alpha is the significance level. You don't know quite what it is yet, but that's a good start, at least knowing that alpha is the significance level. Next, the confidence level is 1 minus alpha. Those are like, BFFs, 2 peas in a pod kind of thing. The confidence level is always based on the significance level and vice versa. Usually we will set the significance level first, at least in the future. But for now, we just need to know the 2 of them go together. Lastly, so our 3rd new concept here is a critical value, but it's actually something that we've done before, which is kind of nice. A critical value is the z-score, t-score, or chi-score values on the distribution that correspond to the given significance level. I am pretty positive that right now this statement doesn't have any meaning to you yet, but we're going to bring all this together. But these are our 3 pieces that we really need to bring with us when it comes to confidence intervals. Lastly, confidence intervals, so this is more of a general statement, but confidence intervals are always centered around the point estimate based on area. This is really important. When I taught this lecture, I actually underlined this twice. So it's not based on, anything else besides area, 50-50 kind of area. If the distribution is symmetrical, the point estimate is the average of the 2 numbers. So we'll practice this within each section that covers specific parameters. If the confidence interval is not symmetrical, it's going to be a different case and a consideration that we'll have to make. But honestly, I find finding the non-symmetrical confidence intervals to be a little bit more straightforward, but that's just my opinion, and you won't get to decide until we get to topic 8. So we are going to be finding confidence intervals on the mean, standard deviation, and proportion. But you can find confidence intervals on any parameter at all whatsoever. However, we did see that the median is extremely ill-behaved. So generally, if someone came to me and said, hey, I was looking to estimate the median for this, it's pretty likely that I would tell them that in my professional capacity that I wouldn't recommend doing the median at all. I would probably want to find some other method. I'm sure there's a method out there that exists that you can find a confidence interval for a median, but it's not something that's, kind of widely accepted. It's something that would be a little bit more experimental, let's call it. Range is also pretty iffy. I wouldn't do anything using range. But as I said to begin with, we're going to be doing proportions, which is topic 6, mean, which is topic 7, standard deviation, which is topic 8, and then we have a topic 9, which is estimating sample sizes. In Unit 3, we will be finding all confidence intervals by hand. If you learn of another way to find confidence intervals, you are not going to be able to get full credit on the exam. On the previous exam, if you had some shifty way, not shifty, but if you had some other way that you had found confidence intervals or binomial distribution values for, I didn't care as long as they were correct. But in Unit 3, I'm going to be a stickler on this one. You need to do these the way that we do in class because it's your best bet at understanding the full process. Anyone can just plug numbers into your calculator and get numbers out, but if you don't understand confidence intervals well enough, you'll never be sure if your answer is in the ballpark or if it's, way out there. In Unit 4, we use confidence intervals again, but we use all of them, we get all of them with our technology. So it's a nice trade-off. We earn our right, and then in Unit 4, we get a chance to just use technology to find them. So the parameters that we will be estimating will follow the normal distribution, which now has a new name. Really annoying probably, but it just is how it is. The normal distribution also is called the Gaussian distribution. Even throughout my master's program, I didn't call it the Gaussian distribution, but if you Google it, it will be there. The t-distribution we'll find is not really too new and interesting compared to what we already know. And then the chi-square, it's not chi like your t, although if you said that it wouldn't be too outrageous, but it's the chi-square distribution. So these are going to be, the t and chi-square are going to be two of our new pictures coming up. So as mentioned previously, we have two new distributions. The following slides are going to break these down into all of our new components that we need to know about them. I'm telling you now that on the exam, you will need to answer questions about these distributions. So I would recommend getting to know these distributions a little deeper than, initially you might think. The t-distribution, but before I forget here, is also known as students' t-distribution. Students doesn't come from the fact that it's you're a student and technically I'm a student. We're all students, right? If we're learning, it's just the guy that came up with this distribution. He's like, hey, the normal distribution is too precise. So then I don't know. You can Google it if you really wish to. So let's learn about the t-distribution. The t-distribution is a lazy normal distribution. I would say end of story, but that's not quite it. It really is, however, a lazy normal distribution. They are both bell-shaped. They're both symmetrical, also, which isn't an item down here. Their bottom axis goes from negative infinity to positive infinity. But the t-distribution is heavier in the tails. And so what we'll find is that when we look at this picture of the normal distribution compared to the t-distribution, there's way more area along the outside here. So the normal is pretty tight to the middle, whereas, like I said, it's a kind of a lazier, more relaxed distribution. Honestly, the z-distribution isn't something that I would use if I had a choice between z and t, because the z is going to give us that wiggle room that says, hey, maybe we don't quite have the precision of the normal distribution. But it's not a choice that we make personally. It's a choice that we have to make based on evidence. So we'll talk about that. Each sample size has a different distribution, which is a new concept to us right now, but we'll see on the next slide exactly what that means for our lives. And then lastly, as the sample size increases to infinity, the t-distribution eventually becomes the normal distribution almost exactly. Think central limit theorem, that magic rough cutoff of 30. That will come back and that will be involved in this as we go forward. So this is a sample picture of the student's t-distribution for 4 different sample sizes. Just a quick note, DF is something that we're going to need in the future, but for now it just means 1 less than the sample size. So this has a degree of freedom of 2, so that kind of medium blue color is in the middle. And as we increase our degrees of freedom, so the red one gets closer up to the top peak, the purple one is closer even yet, and that blue curve over along the top, that is the standard normal distribution. Well, for this reason, every single t-distribution actually has a slightly different shape, but we're always going to just make the same bell curve shape anytime that we have to draw a generic picture. So, first, with a lower degree of freedom, we're kind of floating in the middle. So this is a sample size of 2. And the further and further up that we get towards 30, the closer and closer we get to the normal distribution. So, and this is basically because that same reason, the closer we get to 30 or higher, the more our data becomes bell-shaped in general. So now let's look at the chi-square distribution. This is a very, very wild looking picture, but what this is this is actually 10 different chi-square distributions. Something interesting that you probably wouldn't hear in a regular intro class is that the chi-square distribution is the normal distribution squared. There is a reason for this. If you are interested in knowing maybe the background or theory interests you, please shoot me an email and I can give you the explanation as to why. And it's not really that bad, but it's not something that I would choose to include in the class on its own. But it's the normal distribution squared. It's right skewed. So if you look at all these except for this first one's kind of unusual for this one. They kind of have a hump and they skew to the right. So I'm looking at this pink one right now. They have a hump, skew to the right. Turquoise one, it's got a hump, and then it skews to the right. Now, this should also seem similar if you remember to topic 4, what those standard deviations looked like. So if you remember, they had a little peak and then they tapered off to the right. So that's I guess it's a hint, if you will. Now, before I display the next one, if this is the normal distribution squared, and the normal distribution's bottom axis goes from negative infinity to infinity, well, the bottom axis on the chi-square distribution has to go from 0 to infinity, because if we're always squaring the values of the normal distribution, we're not ever going to have any negative numbers, because whatever it is negative, we square it. So then the third bullet here, just like the t-distribution, the chi-square has a different picture for every sample size. The chi-square distribution changes a lot more than the t-distribution does. We're not going to nitpick on any of these graphs at all, but you will be responsible for the items in the bullet. And this is a coincidence too. Well, it's not a coincidence, but not all distributions are going to do this. But just like the t-distribution, the chi-square distribution approaches the normal distribution as the sample size goes to infinity. This is not true of all distributions. There are many, 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 many other types of distributions, and some of them behave standalone, and some of them are related to other distributions. We'll find the chi-square distribution is going to make a new distribution for us later, and it's like, I don't know, like the circle of life or something in stats where, all of these things are related. They're not just coming out of nowhere. And that's one of the things that's cool about stats is we make predictions in a scientific manner. So we are scientific fortune tellers. So now let's take those 3 concepts and 2 pictures and put them together into the pictures that will make up our confidence intervals. This first slide is just a description of the pictures for the next slide. It is a little, I don't know, detailed. So for that reason, I made both a slide and the video talk over for this. So if you want to, you can listen to the lecture. You can put this slide together with the next one or both. So this is the picture version of our 2 confidence intervals for both distributions. It takes into account our 3 terms, the confidence level, the significance level, and the critical value, as well as the 2 different pictures for confidence intervals. Well, first is that the point estimate falls smack dab in the center of the distribution. So the point estimate is going to be here such that 50% of the area is to its left and 50% of the area is to its right. With this non-symmetrical distribution, we find the same thing is true. We have the point estimate here where 50% is to the left and 50% is to the right. Next, our confidence level is the amount of area that surrounds the point estimate. So for this left picture, we have this much area evenly distributed, half to the left, half to the right for whatever our confidence level is. So let's say it's 95%, then half of it would be to the right, half of it would be to the left. Similarly, for our asymmetrical picture, we have half of it to the left and half of the area to the right. So this one just kind of keeps going on, so it's a little bit harder to visualize. If we are 95% confident that whatever is left over is how much error we're willing to allow in the tails. So we'll have half of alpha over here in the left and half of alpha over here in the right. And it's the same thing with the other picture over here. In that moment that's right in between where the tail stops and the confidence interval starts, that's called the critical value. I would take a minute and pause the slide and see if you can, I don't know, maybe recreate or explain these pictures. However, for now, this is pretty vague still. In the next 3 topics, we're going to very specifically look at examples for specific parameters, and we'll get a chance to look at exactly how these pictures work when we have numbers within them. We will also get a chance to practice on this next slide here. So these are the 3 pieces on top: this confidence level, significance level, and critical values. And so this says assume that the parameter follows the normal distribution. So if we are 92% confident, how quote unquote, air quotes, unconfident are we? That's the significance level. So I'm actually going to click and display the answers. If we're 92% confident, then that means we're going to be 8% unconfident, which is our significance level, or how much error we're willing to allow. I would do the critical values last. I would eventually go to that, but I would form this picture first. So the picture is going to have a point estimate smack dab in the center. It will have 92% of the area surrounding the point estimate evenly. And then the remaining 8% will be split between the left tail and the right tail. So overall, this would be 100% of the curve. This critical value of negative 1.75, we've already found before using the z-tables, or the normal distribution tables. So you would need to find 0.04 in the tables, and you will end up getting a z-score of negative 1.75 that has 0.04 area to its left, and then 96 to its right. I'm going to leave the second one for you to try. Please make sure that you can do each of these, but like I said, we will get a chance to kind of cement some of these concepts when we get to the actual specific topics for the parameters. There are 3 different ways to write a confidence interval. So I'm going to display all 3 of these here because all 3 of these are a different way to write the same confidence interval. The reason why I show you all 3 of them is this is the way that we're going to write them most often. However, very often it is helpful to write them this way. It gives us a better understanding. This third way is how they're typically written in articles, is what I find. So in general, they're the lower number and the upper number. So with this first example, we have the lower confidence interval level, a comma, the upper number, and then the values are in parentheses. You could also write them with your point estimate plus or minus your wiggle room, which is also known as your margin of error. We will be calculating margins of error specifically to individual questions in future topics. Lastly, this is a variation of the first one. We will also be putting our lower number, a less than sign, the parameter we're estimating, so this would be a proportion for a population, a less than sign, and then the higher number. Lastly, there are 2 different ways to interpret confidence intervals. The first one is the statistical interpretation, which we will spend a decent amount of time on in the future, making sure that we understand. Then we will also say an English interpretation, which is kind of more for the common person, how we would explain a confidence interval to them. We will be interpreting confidence intervals for almost every single problem that we do in the future, but for now, we are just going to go through a generic version of it just to keep all of our general confidence interval information together in one topic. So the statistical interpretation says that if repeated samples were taken, So I took a random sample from the population, you took a random sample, and everybody else in the intro stats class took a random sample. 95% of those confidence intervals will contain the true value of the parameter. So this would be the population mean mu, and each of these blue lines represents confidence intervals for samples. So one of these falls so far outside that it doesn't have the population mean inside. This was still calculated correctly. It still had, a random number generator used, but it just quite didn't have the true value inside. And this is what we expect to happen. If we wanted it to be 100% accuracy, then our intervals would have to go from negative infinity to infinity every time. Finally, we have the English interpretation, which says that there is a 95% chance that the confidence interval contains the true value of the parameter. So you actually can't say this the other way around, and I'm not going to say it so that nobody gets mixed up, but the population parameter does not change. It's a fixed number, and usually we don't get an opportunity to know what it is. But there's a 95% chance that our confidence interval will end up having that value inside. So coming up in the next topics, we will get to a chance to look at some specific examples. Starting with topic 5, we will be finding confidence intervals for population proportions. As always, if you have any questions, please send me an email.